This podcast is going to take you through the process of how to determine Lewis dot structures for molecules. Lewis structures are two-dimensional sketches that show the arrangement of atoms and electrons in a covalently bonded species. In a Lewis structure, each atom in a molecule is represented by the atomic symbol for the element. Each pair of shared electrons or bond is represented by a dash, and non-bonding or lone pair electrons are depicted using dots. Lewis structures cannot show the shape of a molecule, they are only two-dimensional. We will determine the shape of molecules using the Vesper theory, which will come later. Now, the reason why atoms are bonding is to satisfy what is known as the octet rule. So atoms form bonds in order to have 8 valence electrons. What I've shown here is the periodic table, and above each group the number of valence electrons that that particular group has. So if we look with the alkali metals, they all have 1 valence electron, as does hydrogen. The second column, the alkaline earth metals, they all have 2 valence electrons. If we skip the transition elements, we're just looking at the main group elements here. The boron family has 3 valence electrons, and we represent that over here in this column. The carbon family has 4 valence electrons. The nitrogen family has 5. The chalcogens, or the oxygen family, they have 6 valence electrons. The halogens have 7 valence electrons, and the noble gases have 8 valence electrons, except for helium, which only has 2 valence electrons. Now, to draw the Lewis structures for elements, we do this, and I apologize for the fuzziness in the image, but I took this from the textbook. So these are the Lewis structures of main group elements. What you do is you draw the symbol of the element that is in question, and then you show the valence electrons for that element as dots. So that first group, that first column of elements has 1 valence electron, so we would show it as 1 dot around on the side of the atom. The second column has 2 valence electrons, so there are 2 dots. And then we skip over, and there's the 3 valence electrons. Here's the 4. And then we have the 5, 6, 7, and 8. Notice that the element is sort of like the face of a clock, and you fill in the valence electrons using dots. Okay. There's no more than 2 dots on each side. And these represent the valence S and P electrons. Now there's something called the honk rule when determining Lewis structures, and I found a short video clip I want to share with you about the honk rule. So honk if you love chemistry. Honk. Let me switch into that here.
When drawing Lewis structures, we rely in large part on the octet rule, but I also find it useful to teach students the honk rule. Now understand these are rules, they're not immutable laws of science, and so there are going to be exceptions. Nonetheless, most of the time these rules apply, and they help us in deciding how many bonds will be around any given atom in a covalently bonded compound. So it goes like this. Hydrogen and the halogens will form 1 covalent bond in covalent molecules. Oxygen and the oxygen family, meaning the non-metals in the oxygen family, will tend to form 2 bonds. Nitrogen and the members of the nitrogen family, in particular phosphorus, will tend to form 3 bonds. Carbon and the carbon family, in this case limited to silicon, the only other non-metal, will tend to form 4 bonds. If you look at the periodic table above, we have hydrogen and we have the other non-metals, excluding the noble gases, which tend not to form covalent bonds. So let's look at how this is useful in drawing Lewis structures. So hydrogen in a chemical compound will tend to have a single covalent bond. Because hydrogen will only end up with 2 electrons around it, that bond, which is essentially 2 shared electrons, will suffice. The halogens, on the other hand, we'll take chlorine as an example. The Honk rule says chlorine will form a single covalent bond. To get its octet, it's going to have 3 pairs of electrons that are not shared covalently. And that will be true for the other halogens as well, fluorine, bromine, iodine. The members of the oxygen family tend to form 2 bonds. Now there's 2 ways that that can happen. Oxygen could have 2 single bonds, and that would necessitate 2 pairs of unshared electrons, 2 unshared electron pairs. Another possibility is that oxygen could form a double bond with one other atom, and again, we're going to get 2 unshared pairs of electrons. Nitrogen, in the nitrogen family, tending to form 3 bonds, can do that 3 different ways. Nitrogen could form 3 single bonds, which would require 1 unshared pair. Nitrogen can form a double bond and a single bond for 3 bonds total and an unshared pair. Or nitrogen can form, as it does in hydrogen cyanide, a triple bond and 1 unshared pair. Notice there's some generalities here. The halogens are always going to have 3 unshared pairs around it. Oxygen, 2 unshared pairs. Nitrogen, 1 unshared pair, which should lead to the conclusion that carbon will not have any unshared pairs in most covalent compounds. So carbon's possibilities are going to look like this. Carbon can form 4 bonds. It could be 4 single bonds. That gives it an octet, no need for unshared electron pairs. Carbon could form a double bond and 2 single bonds for its 4 bonds. Carbon could form 2 double bonds, or carbon can form a triple bond and a single bond. There's no such thing as a quadruple bond. And in all of those instances, carbon gets its entire octet from the bonding electrons and has no need for unshared electron pairs. That's the usefulness, again, of the Honk rule.
Alright, so that's the Honk rule for generalities here. And what we're trying to do, as he showed, is to satisfy the octet rule. Now, there are some exceptions to the octet rule, and here are the elements that are going to be some of the exceptions to look out for. Hydrogen, beryllium, and boron. If you look at their placement on the periodic table, they're up relatively high, and they won't necessarily have the octet. They'll be satisfied without that. Actually, hydrogen is satisfied with just 2 because it's the s orbital that's being filled. It will be satisfied with a duet. Beryllium and boron are so small that they will be fine if they are only having 6 electrons. There are some elements that can also expand their octet, so they'll take more than 8 valence electrons, and some examples here are sulfur, phosphorus, and xenon. We'll look at some examples while you're doing these diagrams of Lewis structures, and you'll start to see some interesting things develop. Also, radicals. Now, radicals are things that have an odd number of valence electrons. So when we get into counting the valence electrons, if you ever have an odd number, radicals would be something where you'd have an exception. And radicals are the things that do the damage to the ozone layer. So free radicals, where you have what makes it radicals, there's an open spot for bonding to occur, and what it does is it latches on to whatever else it can find and causes havoc. So we don't really like free radicals all that much. They do quite a bit of damage, not only to the environment but also to our bodies. So how do we draw a Lewis diagram? Well, you have a handout that I gave you, and these are some of the steps I'm just going to summarize here. First thing you have to do is find the total number of valence electrons of all the atoms in the chemical formula. Alright, so you need to look at the elements that you're working with and count up the number of valence electrons that you have. And then you arrange the atoms in a skeleton structure. So the singular atom, if there's one atom that's by itself, it's usually put in the middle of the structure. That goes in the middle, and then you draw a skeleton or a sketch and surround it with all the other things that are in the compound. And when you do that, you use dashes to show that you're sketching out the bonds, and those bonds are represented by a dash. So every dashed line that you see in a Lewis structure is actually representing 2 electrons that are bonding. And then you distribute the remaining electrons that you have to give each atom an octet. Now remember, there are some exceptions, so if you're working with boron or beryllium, they'll be fine having less than that octet, and hydrogen will only have a duet. If there aren't enough electrons to go around, then what you will have to do is form double and triple bonds, or triple bonds, not both, but we shall see an example of that a little bit later in this podcast. All right, so let's try drawing one here. We have carbon tetrafluoride. So this is where your knowledge of how to name compounds comes in. So carbon tetrafluoride. You need to know what the formula for that is first. So write that out, carbon tetrafluoride, and it's CF4. So we have one carbon, and carbon has 4 valence electrons with it. And then you look for fluorine, and fluorine is in the halogens, so you have 4 of those, 7 valence electrons. So for this particular compound, we have a total of 32 valence electrons that we're going to work with for bonding purposes. Okay, so we've just figured out the compound and how many electrons. Now we'll draw the skeleton. Okay, so I have carbon. That I only had 1 carbon, so that goes in the center, and then I surrounded it with fluorines, and I have drawn single bonds here to show that the carbon is connected to the fluorines. When you do that, you use up 2 electrons for each bond. So far I've used up 8 electrons in my bonding. Okay, so now I have 24 electrons left. And what I do is I put dots around the fluorines to give them octets, because right now each fluorine only has 2 electrons and it wants 8. All right, so fill it in there, and we now have each fluorine has an octet. And when I did that, I put 6 dots around each fluorine, which gave me a total of 24 electrons. So there we go. That is my Lewis structure for carbon tetrafluoride. Fluorine has an octet. Carbon has an octet. There's 2 electrons here, 2 electrons here, 2 electrons here, 2 electrons here, total of 8. And every fluorine is satisfied as well. So there we have it. I didn't use any more electrons or any less than I started with, so this is a complete Lewis structure. All right, let's try carbon dioxide. So again, you need to write out the formula for carbon dioxide, and then total up the number of electrons that you have. So carbon's our first element. There's 1 carbon in the formula, so we have 4 electrons there for carbon. And then oxygen, if you find that, figure out the number of valence electrons that oxygen has. There are 2 oxygens in this particular compound because of the di prefix. So we have a total of 6 times 2, so 12 valence electrons. Add those up, we have 16 valence electrons for this molecule. All right. Now, in this case, we have CO2. There's 1 atom of carbon, 2 atoms of oxygen. So if you remember the honk rule, the carbon is going to go in that middle, and there's only 1 of them. So there we go. There's our beginning of our skeleton. And I'm going to put some single bonds in there, and when I do that, carbon right now has 2 valence electron, or 2 bonding electrons, and 2 bonding electrons there, so I used up 4 electrons by doing that. So I have 12 electrons left over. So if I put those remaining 12 on the oxygen, so each gets 6, that makes the oxygens satisfied in their octets, but carbon is lacking. It needs some more electrons. And I can't just draw in more dots for more electrons because I don't have any more. So this is the case where we have to decide, we're short. So we have to try doing multiple bonds. Okay, so if I do that, if I take away a set of electrons from each oxygen, and instead of having them as dots, as lone pairs, have them as shared pairs, let's see what that does for us. Okay, so when I do that, I've done the same to each side. I have each oxygen now has 2, 4, 5, 6, 7, 8 electrons, and the carbon has 1, 2, 3, 4, 5, 6, 7, 8 electrons. So the oxygen and the carbon both are satisfied with their octets. Right? We can also draw Lewis structures for polyatomic ions. To find the total number of valence electrons, what we do is add 1 electron for each negative charge that you have, or subtract 1 electron for each positive charge that you have. You'll draw the Lewis structure and then place brackets around the ion and label the charge on the outside of the brackets. Okay, let's look at an example here. So here we have perchlorate, ClO4 1 minus. All right. There's 1 chlorine with 7 valence electrons, and there are 4 oxygens, 6 electrons each, for a total of 31 electrons. However, this would be a radical, but there's a negative sign there, so -1. So we're going to add that. So we have a total of 32 electrons to deal with in our bonding. Now we just do it like we've been doing these already. The central atom in this case would be chlorine, because there's only 1 of them, so that goes in the middle, surrounded by the 4 oxygens. Okay, when I do that, I use up 8 electrons, and now I have 24 left. So if I put 6 around each oxygen, that makes each oxygen's octet satisfied and chlorine is satisfied. But to show that I had an extra electron, to show that this is charged, I put brackets around it and I put a negative sign on the outside. We can do the same for ammonium. This is NH4 1+. So nitrogen has 5 valence electrons. Each hydrogen brings 1 with it, and that's a total of 9. Oh, odd number, but that plus sign means we take 1 away. Remember, it's a positive thing to get rid of them. So we have 8 valence electrons. Right? So to draw the Lewis structure, we put which element in the middle? Nitrogen, I hope you said. And then we surround it by hydrogens. When I do that, I've used up 8 electrons. I don't have any left over. Is that okay? Yeah, because hydrogen is only satisfied with the duet. Nitrogen has its octet. However, to show that we lost an electron in the mix, we have to put brackets around it and that charge. Okay. Now, sometimes we have what are called resonance structures. Resonance structures are molecules that can't be correctly represented by a single Lewis diagram. So the actual structure is really an average of all the possibilities. What we do is show the possible structures separated by a double-headed arrow. So the example I have here is ozone. Now ozone is a lopsided molecule, it's O3. If you see here, we've got 3 oxygen atoms, but there's no rhyme or reason as to whether or not it's on the left-hand side or on the right-hand side of this middle oxygen. So what we do is we draw a double-headed arrow to show that really this double bond resonates between the left side and the right side.